And what about subsequent Marxist thinkers who also had some pretension to be philosophers, like Lenin, for example?
Well, I think they're uneven. Lenin, I think, is on the whole one of the worst. He says, for example, the theories are copies of motion. I mean, there you have the copy theory of science just copying off the reality in its crudest view. Mao is more sophisticated. Mao is very influenced by John Dewey, who was widely read in China in the 1920s.
Do you think it's actually made a contribution to the subject as it is today, or not really?
I think that it anticipated, it perhaps might have made a contribution if people had been less ideologically divided, because I think non-Marxists could have learned. The Marxists were among the first people to try to somehow combine a realist view with a stress on practice, with a stress on corrigibility, and they were very hostile to the notion of a priori truth. And today many mainline philosophers of science are very hostile to a priori truth. As it is, they play somewhat the role in philosophy of science, I think, that Keynes said they play in economics. He described Marx as one of his sort of underground predecessors.
Yes. When I was introducing this program, I mentioned not only the philosophy of science, but also the philosophy of mathematics. And before we close, I would like us to say something about that anyway. I suppose one can really say that the central problem in the philosophy of mathematics is a direct parallel to the central problem in the philosophy of science, namely, how does it fit the world? With science, it's how does science fit the world? In mathematics, it's how does mathematics fit the world? Is that right?
That's right, and it's even worse, because if you're trying to defend a copy view, a correspondence view of truth in empirical science, you can answer the question, well, how do we build up this picture in such a way that it corresponds? By saying we have sense organs. As I mentioned before, that's not a total answer because there's a tremendous amount of interpretation involved in simple seeing and simple hearing. But if you're talking about numbers and sets, and someone says, okay, if mathematical knowledge is simply some kind of a copy of the way numbers are and the way sets are and the way other abstract objects that mathematicians study are, the question then, what sense enables us to see how they are?
What is a number? Yes. A deeply problematic question, but still an important one.
That's right. And on the other hand, I don't want to say that the anti-correspondence view has it very easy either. It seems to me that mathematical knowledge is a real puzzle. And I think that philosophers should concentrate more on philosophy of mathematics than they do now, because it seems to be an area where no theory works very well.
Isn't there another very important parallel between mathematics and science? I mean, throughout the history of science, one of the conflicts has been between one camp who thought that it was all about objects in the world which existed independent of human experience, and another camp which thought, no, it's human beings and observers who actually contribute most of this. And as you pointed out much earlier in our discussion, the truth is almost certainly a combination of both. There is a long-standing dispute in mathematics, isn't there, between one body of people who think that mathematical knowledge is something that's, so to speak, inherent in the structure of the world, and we derive it from the world by experience and observation, and another body of mathematical thought that says, no, mathematics is a creation of the human mind, which we then try to impose on reality, like a grid, as it were, on a landscape. Isn't that so?
That's right. The latter story is attractive because of the sense organ problem, but it doesn't seem to work either because it seems that we're not free to impose any mathematics or any logic we want. Almost anyone would admit that at least you have to be consistent. And what's consistent and what isn't somehow something we can just make up or decide. As when we try to stress conventionalist accounts, subjective accounts, we come up against the objectivity of mathematics. When we try to stress the objectivity of mathematics, we come up against another set of problems. I think we can learn a lot more than we now know about human knowledge and about scientific knowledge by going further into this area.
Talking of where we're going from where we are, so to speak, I think the most interesting way in which you could end this discussion, Professor Putnam, would be by talking about what you regard as the most interesting problem areas of the moment, and therefore, I take it, the most likely growth areas for the immediate future in both of the subjects we've been discussing, philosophy of science and philosophy of mathematics.
Okay, I think that if I'm allowed to confine my prediction to the immediate future, because we know that long-run predictions are always false.
Yeah.
But in the immediate future, I would expect philosophy of mathematics to be a growth area and philosophy of logic. I would expect philosophy of physics, I think, to decline somewhat from its central place in philosophy of science, although I think part of it touches philosophy of logic. The question, the astounding suggestion, has actually come forward in connection with quantum mechanics, that we may have to change our logic, our view of what the true logical laws are, in order to really understand how the world can be quantum mechanical. And I think this side of philosophy of quantum mechanics, that touches philosophy of logic, will be a hot discussion area. But more generally, I think areas which we almost don't think of as philosophy of science, that become philosophy of language and philosophy of mind, like these questions about computer models of the mind, computer models of language, and these more general questions about theories of truth, the nature of truth, the nature of verification, how science can be objective even though there's not a rigorous scientific method. I think these questions will continue to be the staples of the field.
One thing that worries me about this whole area is its relationship to the educated layman, I mean, which in a sense is the person our discussion has been for. After all, it's now over 70 years since the 25-year-old Einstein published the theory of relativity, and I'm sure you'll agree with me that it's true to say now that the great majority of educated people with higher educations, university degrees and so on, still have scarcely any idea of what this is all about, and it's done very little to actually influence their view of the world. Isn't there a danger that now science and mathematics are simply racing ahead, and the whole new range and world of insight that is giving us into the universe in which we live simply isn't filtering through to the non-specialist, or not filtering through anything like fast enough?
That is a danger, but it's one that something can be done about. There's now, for example, a text of special relativity called Space-Time Physics, which is designed for the first month of the first freshman college physics course. And the authors say at the beginning that they look forward to the time when it will be taught in high schools.
And do you think that time will in fact come, and quite soon?
I'm sure of it.
Yes, well, I think you're right, and indeed I hope you are. Thank you very much, Professor Putnam.
Thank you.